So let's continue. Last time, we started to introduce the linear response function, and by using linear response theory, we are able to get the physical observables that we want to measure in terms of the Green's functions or correlation functions up to the linear order in your small perturbation. And this small AC field, V of t, is a time-dependent AC field, which is written in this form, V0 e to the minus I omega t. And this is a small perturbation or a small field that you apply to the system in order to get some response. And you get some response in the presence of that small perturbation. And you evaluate the difference between this observables A of t with expression value, the difference between this expression value of the A of t in the absence of this field and in the presence of the field. It's called this delta expression value of A of t. And this is written in terms of this A0 as constant prefactor times e to the minus I omega t, with A0 is the product of this V0, which is the prefactor or strength of your perturbation, times some response function k omega. And this k omega is the time Fourier transform of this k of t, and this k of t is your time correlation function of what you are measuring. And there is a correspondence between frequency dependence of such a linear response quantity, and in the real-time domain, there is a corresponding function, which is a convolutional time integration over t prime, and you start to turn on your perturbation t prime 0, and before that, there is no such a response because you haven't applied your external field yet, but you turn on this field at t prime 0, and then you convolute all these contributions after you turn on the small perturbation, and this kernel function k is a function of t minus t prime, which is a retarded function of your linear response. Okay, so these two are Fourier transform in time domain, and we will derive such a relation between this k omega and these correlation functions that you are trying to measure. And to measure this, or to calculate this correlation function, so we should start from the Hamiltonian, which consists of just a non-perturbed H0 part plus this small perturbation. The small perturbation, is a term that couples this weak external field, AC field, to the some operator B, and this operator is what we are trying to study. For example, if this V of t is a magnetic field, it's, the AC magnetic field, then this B operator is the spin density, because this is just a B dot S or S dot B. This is kind of a Zeeman energy, and if V of t is a vector potential, then this B operator should be the charge current. So the current coupled to this vector potential, and the spin density coupled to the magnetic field. So we will discuss these two cases in just a moment. So suppose that when t is less than 0, in the past there's no such a perturbation, V of t is 0, and the system has the eigenstate psi I and eigenenergy E of I, which satisfy this time-independent Schrödinger equation or eigenvalue equation for H0. So now let's start to turn on this perturbation V of t at t equals 0, and we apply time-dependent perturbation theory in quantum mechanics, assuming that this is a small perturbation, and then we follow this quantum mechanics to write down this eigenstate at a later time greater than 0 of t, and this psi I of t is expressed in terms of the unperturbed eigenfunction with the time evolution plus this small correction, and that small correction comes from this, this small perturbation V of t, okay, that coupled to this B operator, and therefore you get this type of corrections. And also we neglect this high order, this V square terms here. So we only keep up to the linear order in V, and that's why we call this linear response, because this is the response up to the linear in external field. So let's just use the abbreviate shorthand notation for this psi I, this unperturbed eigenstate. So delta A of t expression value. So sorry, this is I at time t. So this kind of a small amount of response difference is defined as the difference between this expectation value evaluated at t equals 0 or less than 0 and this same expression value evaluated at time t, or vice versa. So do it either way. So let's just start to calculate this expression value at time greater than 0 of any operator A, and you immediately get this unperturbed plus. Okay, so you simply just plug in this definition of this expression value of this A operator. A is some other operator which is related to B operator, which we will discuss and define in just a moment. By definition, so you simply just plug in this new expression value evaluated at time greater than 0, and this new eigenstate psi I of t following this time-dependent perturbation theory is here, right? So the first term is a non-perturbed eigenstate with the time evolution. The second term is the correction term up to the linear order in the small perturbation, and multiply all this matrix element that you could derive, and check from your quantum mechanics textbooks. In time-dependent perturbation theory, then you plug in this new eigenstate here and there on the left and right side of this operator A, and you get 4 terms, right? So you keep this psi I of t up to linear order in V, so you get the zeros order and the linear order. Okay, so this is true for this Dirac-Bragg state and Cat state. So you get 2 states on the left and 2 states on the right. So in general, you get 4 terms, but you only keep the terms that are linear in V, and you forget about all the higher order term that higher than V linear. So the first term is the non-perturbed expression value. This is precisely your A of t evaluated at 0 time or initial time. And there are 2 additional terms which come from this linear order in V corrections, and you see this kind of a sign change relative to these 2 different terms. You get different states. One is the Bragg state, another is the Cat state, and these 2 states are Hermitian conjugate to each other, and therefore you get m plus 1 over I here minus the other term, and also you get a minus I here in the exponent of this exponential time evolution, but this is a plus for the other term. So the plus and minus term reflect the fact that one of the states is Dirac-Bragg state, another is the Cat state. And so you forget about this V square and high order term. So you simply just combine these 2 contributions and plug in this definition of this small shifts of your expression value of the A operator. And you'll see that this will lead to some kind of a commutator. The first non-trivial term, linear in V, starts with the A matrix element A operator, and then B on the right. But the second term starts with the B matrix element and then A matrix element later. So this is AB, but the second term is BA. So you got AB, something like AB minus BA, because there's a minus sign here. So you'll see that this, when you combine these 2 terms, you get something proportional to this AB minus BA, which is precisely this commutator between A and B. And this commutator between A and B is precisely what we are trying to measure. So we're trying to measure the correlation function between A and B, and also B and A, and you simply just subtract one from another, you get a commutator, which you will measure and which you will calculate. So the A operator, in many cases, corresponds to exactly the same as the B operator. Okay, so if you're interested in studying magnetic properties or spin operator of your system, then your A operator could be something that you want to measure, but this, say, for example, the spin, and this B operator is also spin if you apply the magnetic field. So A and B are something proportional to each other in most cases. For example, you want to calculate and measure this charge current and up to linear order in your external vector potential. So you'll find that A and B are simply just proportional to the charge current. So what you measure and calculate is nothing but current correlation function. So we will come back to this in just a moment. So let's take a short break, and when we come back, we will continue, to calculate this kernel k omega and k as function of time. So this is an adiabatic turn on. So you don't suddenly turn on this perturbation. But we do not study the quench dynamics of the system. But imagine that we simply just study long time behavior of this correlation function, and even though this could be a quench problem, but we simply we forget about this transient behavior, that's when the system becomes non-equilibrium. So of course you could study the transient behavior, and assuming that this switch on and off for your interaction or small field is a sudden switch, it's a sudden turn on or turn off, but this is a separate problem. We are simply very naively consider a situation where you turn on some small field at time equals 0, and you study a long time correlation of those operators. So let's just continue, finish up this derivation. As you can see that when you collect all this linear term in V in your linear response function, this delta expression value of A operator as function of time could be expressed in terms of the time convolutional integral over dt prime, and inside this integrand you get V of t prime times this kernel k function as function of t minus t prime, right? Because when t prime is 0 or less than 0, you get no response, but this is only happening when t prime is greater than 0. And then this kernel, as I just showed last minute, that this is given by AB minus BA. But we have two independent integration over time. But then due to the causality, there's a theta function here to guarantee that t has to be greater than t0, t prime. Theta of x1 if x positive and 0 if x is negative. Okay, because we need to preserve this causality that nothing happens when small perturbation has not been applied yet. But this integrand consists of this commutator-like operator, and then you should take the expression value of such a commutator between A of t and B of t prime. But at finite temperature, you need to take a thermal average or ensemble average, and that means that you need to sum over all possible initial state, and also you should insert a Boltzmann weight, a thermal weight function, which is e to the minus beta ei divided by the partition function. So by standard definition, this kind of expression value is a thermal ensemble average expression value of this commutator, and then you put on this causality condition that this occurs only when t is larger than t prime. And this is a kind of correlation function, or the Green's function. So let's just elaborate this commutator between A and B by the following examples. This response in the magnetization mz to this field hz, or magnetic field along the z direction, is going to be this correlation function where you take both A and B, the same operators. So which means that if you want to measure the magnetization change due to the external AC magnetic field, then this response up to linear order in your field is proportional to this expression value, a thermal average of your commutator, and inside the commutator, and these two operators are identical, which are simply just magnetization along z directions at time t and at time t prime, meaning that what you calculate and measure is the correlation between the same magnetization operator at two different times, t and t prime. And this is going to be mz of t minus n times mz t prime minus the other. Of course, this is non-zero, because remember, this mz in quantum mechanics is operator. So of course, when you take the spectrum value of this same operator at different times, you get the different thing, because the order matters. This mzt appears on the left-hand side, and then mzt prime on the right-hand side is not the same as the other order. So that's the magic of quantum mechanics, that you get a non-zero commutator between any two quantum mechanical operators when you take the expectation value. So this is non-zero, and this is something that is measurable and calculable. And we successfully derived this kernel K. So let's just take another example. So if you like to know this conductivity or resistivity, in general, you need to calculate this conductivity tensor, sigma alpha beta, which is a function of space and time. And this sigma alpha beta is determined by this kernel K, which is a current correlation function. So if you apply the AC electric field or vector potential, what you study is the electrical property or charge transport of your system, and up to linear order in your vector potential, so you will get this response function K proportional to this current correlation function. It's a commutator between these two current operators, J alpha and J beta, and alpha and beta could be X, Y, or Z. In other words, you could, measure these correlation functions between two current operators at different space and time coordinates, RT and R prime T prime. Of course, you simply just by the same argument, you know that this is certainly non-zero because both are quantum mechanical operators and along different axes. But you can also calculate this J alpha or J beta, which is the current correlation functions along the same direction. But in general, you could calculate current correlation function along different directions once you apply a vector potential along any direction. So as a result, if you would like to study electrical property or charge transport of your materials, what you want to do is to apply the AC vector potential. And then you pick up this small deviation of your expression value of the operator up to linear order, and this small deviation in the observable is proportional to this current or spin correlation function. And then this is the relation between the linear response and the Green's function. So we will study how to calculate this spin correlation or current correlation function in the specific examples later on.
Yeah. First one, there is no spatial particle correlation, so it means it's a homogeneous system.
Right. So you could either probe, this current correlation function on the same spot. You can also calculate correlation across different locations. That's your choice. I can fix this R prime to be R, or vice versa. I only study the spatial correlation by fixing the time. So in general, you can have three different cases, right? Either you fix space or you fix time, or you relax, or you allow the space and time, or both different.
And so in general, what the magnetic field, that case is also can be function with R, right?
Yes, of course. In general, yes. Is that clear? So I hope everyone really understands the connection between the linear response and correlation function. So we will define the single particle Green's function, or this transition amplitude or probability amplitude, to move a particle from one space and time to another one. And then we will try to build up all this Green's function and to calculate this spin or current correlation, because the spin and current is nothing but a function of those single particle Green's function. So we will define the single particle transition amplitude or Green's function, and then the more complicated operators such as magnetization or the charge current operator is nothing but a function of this single particle Green's function. So everything is reduced to this Green's function for a single particle, even though what you calculate observed is more than single particle physics. But later we will show that all this complicated object could be reduced to a complicated function of the single particle Green's function. Even though this is a many-body system, but they could be reduced to collection of many single particle Green's functions. So it is the single particle Green's function in the background environment of the many particle. So let's just introduce the third example of this Green's function, which could be used to understand the thermodynamic properties or statistical quantities such as free energies or particle number and so on. And those quantities could be measured in the lab and also could be calculated via this single particle or many particle Green's functions. But we will define formally this temperature Green's function or thermal Green's function later. We just would like to emphasize the connection between these two. So I'm skipping the definition of the thermal Green's function because we will define the thermal Green's function in just a moment. But let's just look at this total number of particles. So in many body systems, if you like to calculate the total number of your particles, for example, the electrons, what you can do to perform such an integration over space, and inside the integrand, you sum over all such a single particle Green's function states alpha, G0 alpha. Alpha refers to this kind of a correlation function. So here we introduce this imaginary time correlation for the reason to introduce such an imaginary time in the Green's function will become clear later. But here, this is the necessary procedure to get this finite temperature thermodynamic properties of your many body system. And so your real time will be generalized to the imaginary time, tau equals to IT, where t is the real time, in order to calculate more easily the partition function of your ensemble. And we will define such a single particle Green's function at finite temperature, something like this. But of course, there's some plus minus prefactor depending on whether your system are made of fermion bosons, but never mind. So let me just outline the final results. Once we define this single particle Green's function in the imaginary time domain at the finite temperature, and you simply just sum over this function, especially this imaginary part of this G0, and you get the total number of particles. So, for example, for the fermion case, if you want to calculate this electron number of the system, what you really want to do is to sum over this Fermi function and sum over all this momentum up to this Fermi momentum, and there's a factor of 2 here for the spin, 1/2. But this Fermi function is nothing but imaginary part of this non-interacting Green's function at finite temperature, G alpha alpha, and if you perform the Fourier transform to this momentum space, and this is precisely this Fermi function. So the Fermi function is related to a correlation function of single particle. So meaning you simply just can understand this by considering this kind of operator product, which is C dagger K C K in K space. Namely, if you destroy an electron and momentum K, and then you create another electron at same momentum K, and what you just did is just to count the electron number, because I simply just destroy the electron and then I create that electron again. So I count the electron number by 1 if I do this. Okay, if I evaluate this C dagger KCK at finite temperature, and this is by definition the Fermi function. And the Fermi function, the expression value of this number operator C dagger KCK, if you take the expression value of this number operator, either in real space or in momentum space, they represent the number, thermal average number of your particles. So even though this is very straightforward and trivial, like Fermi function, has a profound meaning in the context of the Green's function, because this is nothing but this, you sum over this G0 alpha alpha over this state alpha and also the space coordinate, and you can know this total number of particles in your system. Of course, you could also do the same thing for bosons. So we will derive such a Fermi, Dirac, and Bose-Einstein distribution function based on the Green's function method. The lesson to be learned is that the particle number is a function of Green's function. And I guess this is for boson, this is for fermion. And let me just tell you another example of this Green's function to prove the total energy of system or free energy of system. For example, if you want to calculate and observe the thermal average of your Hamiltonian, which is nothing but this expression value of your total energy which is the sum of the kinetic energy and potential energy of the system. You take the thermal average, and this is an observable quantity, which you could certainly measure in the lab, but this is also a quantity that is proportional to Green's function. So how come? So we will derive this later, but here, let me just switch, just sketch this final answer. This is what you should do if you have just a non-interacting many-body system. And what you should do is to calculate a single particle Green's function. You take the trace. When you take the trace of this Green's function G as function of x tau and x prime tau prime, and you perform such operation, you take the first time derivative, imaginary time derivative, and then you take the second order in space derivative Laplace, and then this chemical potential, and you consider this as just your Hamiltonian operator. You simply just act this onto this the trace of your Green's function. And the Green's function could be, in general, a matrix, and you simply just carry out the trace of this Green's function matrix, and then operate this trace of the Green's function by applying such an operator. So when you have done so, and then you integrate over this whole space, and you take a limit when x prime goes to x, and tau prime goes to tau plus, where tau plus is simply just tau plus some very small number. So meaning you simply just converge this x and x prime and tau prime. In the limit of x goes to x prime and tau goes to tau prime, and you take the trace of this Green's function, and you have done such operation, and then you take the limit, okay, and you integrate over the entire space. And so for boson, you should put a minus sign. For fermion, it should plus sign here. And this quantity on the right-hand side of the equation describes precisely the ensemble average total energy of the system. So the total energy of many-body system at finite temperature is also a function of the single particle Green's function. Okay, so yeah. So even though we have some interactions, V and this identity still holds. Okay, so for example, if we have the Coulomb interaction between two electrons, then this V describes the Coulomb potential, and even in this case, we could still formulate this total energy after taking ensemble average is this expression here, which is governed by the single particle Green's function. Okay, as I mentioned last time, the single particle Green's function tells you this transition amplitude for one quantum particle to move from one space and time location to another space and time location. And everything that you can measure in the lab is related to the single particle Green's function. So we will define, say, two particle or many particle Green's function, where you could simultaneously move two particles from one space and time to another one. Okay? But those complicated two particle Green's function can be reduced to a function of single particle Green's function. Okay, so I guess that's probably enough for the introduction part of this course. And the purpose of this course is to learn how to use this single particle Green's function to describe this many-body phenomena, such as metals and magnetic properties and charge transport properties and the superconductivity phenomena and dielectric functions and this plasma oscillations and whatever you could imagine that you study and learned in elementary solid-state physics. So everything could be expressed in terms of the Green's function. And in some cases, for example, if you like to study these dynamic properties of your dielectric function, so the dielectric function epsilon, or dielectric constant of your metal or insulator, is defined by this prefactor between the displacement field and your electric field, right? But you can study time-dependent or frequency-dependent of this epsilon as a function of momentum and frequency, and this could be observed in your lab by shining a laser or apply an electromagnetic wave, a light wave, to your magnetic or non-magnetic or metal or insulator samples, and you could actually calculate from your data the displacement field and electric field, and you take the ratio at different k and omega, you get dielectric function. But this dielectric function can only be derived within Green's function framework. So it is not possible to derive and understand such this complicated dynamic quantity, dielectric functions of omega and k, in the quantum regime. So you get this formula in the classical regime, but in the quantum region, you should rely on the Green's function method. So no other technique could allow you to really reliably calculate this dielectric function. In other physics as well, so we will give you many examples. Those important physics could be understood only if you know the Green's function technique. Okay, if you don't know the Green's function, and it's really difficult to understand many aspects of many body phenomena. So the Green's function is really the key for the experimentalists and also for theorists to really understand the physics. So let's call it a day, and we'll continue tomorrow.